We present here our experimental and theoretical results on a novel type of modulation of the transition frequency of a superconducting qubit. We call this type of modulation periodic latching modulation. It is defined by fast switching between two values of the transition frequency, with waiting times of half a period at each of these two values. This process, implemented in the experiment through a square wave modulation of the bias line of the qubit, is shown schematically here in the usual avoided crossover representation of the energy levels. This type of modulation cannot be treated by simply employing the standard Landau-Zinner formula for transition probabilities. Indeed, the Landau-Zinner speed at the crossover is in this case infinite, predicting a value 1 for the probability of transition to the excited state for a single transversal. Thus, standard results from the literature do not apply. In one of the theoretical approaches that we developed, we calculate the probability PS of a transition on the sudden switch of frequencies. Use this probability to construct the unitary transformation for a single switch, U right to left, then construct the transfer matrix for many periods, and finally calculate the average probability of being in the excited state. This formalism allows us to identify the resonances and anti-resonances, or coherent destruction of tunneling, of the problem. And here are the results: experiments in the right panel versus numerical simulations in the left panel. The figures represent the excitation spectra as a function of modulation frequency omega for a fixed modulation amplitude delta. The red lines are the anti-resonances, while the resonance conditions are plotted in yellow and gray. Also, the interference fringes are visible in the representation in which omega is fixed and delta varies. Another formalism that explains the sidebands observed in the experiment at high modulation frequency omega is the rotating wave approximation, a method usually applied for sinusoidal excitations. For the case of periodic latching modulation, the pleasant surprise is that analytical results can be obtained. The probability amplitude delta squared can be found analytically, and the results can be compared in a straightforward way with the known result for the sinusoidal modulation. Indeed, the rotating wave approximation matches very well the numerical results and the data in the region of not too low modulation frequency. Also, a comparison with the sinusoidal modulation is made. In conclusion, we demonstrated a new type of frequency modulation in a regime where the standard Landau-Zinner formula is inapplicable, but the concept of Stückelberg interference and phase remains relevant. The experiment was realized by changing the flux bias of a transmon using square wave pulses. Three theoretical approaches, the transfer matrix, the rotating wave approximation, and numerical simulations, have been developed, and the theoretical results agree very well with the data.